Okay, hello and welcome to the second module of lecture 1. So without further ado, let me stop my video and start sharing the screen. Right. So in the previous module, we have seen that the systems can be classified according to various specifications such as open loop and closed loop, which we've already seen in the previous lecture. Then we also saw that systems can be dynamic or static depending on whether the output at an instant given by t is dependent exclusively on the input at that particular instant only, right? Then we saw the difference between linear systems and nonlinear systems. Anything that is not linear is nonlinear, right? So we saw what characterizes linear systems, that is the principles of homogeneity and additivity, together known as the superposition principle. So in this short module, relatively short module, we shall also see what time invariance and time varying systems are and what causal and non-causal systems are. But before that, let me also clarify what these other two classifications imply. One is a continuous time system and a discrete time system. Of course, continuous time system means when you have the system's variables defined at every instant of time, that is for all real values of t. And discrete time systems are those which are defined only at specific values of the time t, right? Some discrete values of the time t. That is when the system's variables are monitored, right? Then there is another classification which may not be very familiar to you, which is between deterministic systems and stochastic systems. So again, for the purpose of this course, we shall always be talking about deterministic systems. In fact, stochastic continuous systems are very complicated class of systems. So what are stochastic systems? Look, when you have a deterministic system, you can basically infer everything you need to know about the system just by knowing the initial conditions of the system and the parameters of the system, all right? On the other hand, if you are dealing with a stochastic system and you know just the initial condition and the parameters of the system, you'll still have what is called an ensemble of possible outputs, okay, rather than a specific output. So typically systems, when they're corrupted by noise, disturbances, or such uncertainties, yeah, then you generally deal with stochastic systems. So within the purview of this course, we shall not be talking about stochastic systems. As I said, stochastic continuous time systems, dynamic systems, they're described as stochastic differential equations. That's they're very complicated class of systems, right? So let me just tick off what we've discussed. We've basically talked about what the difference between deterministic and stochastic systems are. Of course, intuitively also you understand what continuous time and discrete time systems are, right? So let us now formally launch into what is time invariant and a time varying system, all right? So again, let us go back to characterizing a system by something that we call G, all right? So let's say you have an input signal U, which is taken to an output signal Y. So both Y and U, as I said, are time-dependent signals where the arguments are in time, and G is what characterizes the system, all right? So when we say that a system is time invariant, it essentially means that if I'm to draw this figure here, suppose this is your input signal, all right? And so this is basically input, this is the output, and let's say this is your output. Then if you shift the input, let's say this amount of shift is some tau, it so happens that the output gets exactly shifted by the same amount tau. So what is a mathematical way of being more precise with this kind of description? Well, let's say I define sigma tau as the shift operation, all right? So you define sigma tau as the shift operation. So then what does time invariance imply? Yeah, so this is, let's say, u of t minus tau, and this is y of t minus tau. So what it essentially says is, look, for the sake of brevity, we'll just drop these arguments, these brackets that we've used here. So we'll say that when a signal u, again I'm dropping the time here for brevity, but of course these are signals, you know that, right? Because these are dynamic systems, not static systems, okay? So if you do this, this is what y is, right? So y is equal to g of u. So basically g is the system which acts on this input to produce y. Now, if I act on this output, that is I shift this output. So this is basically an operation. That is nothing but shifting this entire thing, right? Because this is nothing but y, yeah? So when you shift the output, that is exactly the same as what would have happened if you had initially shifted the input and then, yeah, and then you had acted on this, right? So if you have shifted, okay, this is the original, so this is the original input, then this is a shifted version of the input. So if you pass this shifted version of the input through the system, you will get the shifted version of the output. What this basically means is that this would be your y, okay? That essentially means what in technical terms we call that this system commutes with the shift operation, okay? So it matters not as to whether you have first shifted the input and then passed it through the system, or you have passed the signal through the system, the input signal through the system, and then shifted the resultant output, yeah? In general, this commutativity of operations, yeah, when you're passing through systems. So shift operation, basically that's also a system maybe that shifts. It's like causing a time delay, right? So this is an original system, there's a time delay added to the system. So in general, for a time invariant system, you see this system and the time delay, they commute. So the order of these operations does not matter. So in technical terms, this is what characterizes a time invariant system, all right? So if this holds true for any system, then it is a time invariant system. Again, quickly try out the following examples before you move on to the next part, okay? So let's say we have first example 1, y of t is given by x of 3t, okay? Second example being y of t is equal to integration from 0 to t square root, sorry, excuse me, yeah, it's a square root of u of t1 d t1. And the third example is y of t is given by integration from t minus 3 to t u squared t1 d t1. All right. So you're required to check whether each of these individual systems, they are time invariant or not. All right. So I'll just take, let's say, the first example, the easiest example, and I'll leave the rest to the other two to you. They're also not very difficult. You should be able to check, in fact. So anyway, let's take the first one, right? So if you're doing sigma tau on yt, what does that mean? You're saying you're doing y of t minus tau. That is what a time shift entails, right? That is nothing but x of 3 times t minus tau. Why? Because whatever you're doing to t on this side must be this. This is exactly how it's defined, no? If yt is equal to x of 3t, then y of t minus tau is equal to x of 3 times overall t minus tau. Yeah? Okay. Now, if I were to pass this, okay, x t, that is nothing but x of t minus tau. Okay, so this is the shifted version of the signal. All right, then what will be the y in this case? Y hat t. Yeah, and you must convince yourself, if need be, with a sketch, but this is what it is. This is going to be nothing but x of 3t minus tau. Notice that this tau does not get multiplied by the 3. Why so? Because this y is, the argument is t, right? Now look at this one here. This is what describes the system, no? Yeah. So whatever happens to, whatever is the argument here, that gets multiplied by t. So that time. So time is the argument here, and only the time gets multiplied by 3. The constant factor does not. Okay. If this does not sound convincing to you, I suggest that you draw a signal. Maybe take the simplest example. Yeah, something like this. So this is, let's say, x of t. Yeah. So the y of t will be something like this. So if this duration is, let's say, t, then this will be t by 3. All right. And then you pass this through a shift operation. So you shift it. Yeah. Let's say this is tau. Okay. This is the time axis. This is the time axis. This is x of t minus tau. This is y t. This is y hat. All right. T. So what happens here? You see that at a point such as this, which is basically nothing but tau by 3, this thing will start here and end here. End at, what is the position of this? It is going to be nothing but tau plus t overall by 3. Yeah, it will span till here. On the other hand, if you want to draw this, yeah, it is easy to see that this whole thing will be shifted by tau rather than tau by 3. So therefore, they are not one and the same. So this is indeed actually a time varying system, not the Scooty DPS, but time varying system. All right. Okay. So along the same lines, I urge you to try these 2 other examples and see if they are indeed time varying or time invariant. All right. The next idea is that of causality. Okay. So what is causality? In layman's terms, or loosely speaking, causality basically implies that the system's output at the present instant cannot be determined by an input applied at some future instant. So basically, the system's present output must only be a function of past and present inputs and not something that you do in the future. Yeah. So basically, if the economy of the country is down in shambles, you cannot say that if you elect me next time, then I'm going to sort this out. At present, the economy is in shambles, it will remain in shambles, okay? No matter what your politicians say, even if they ask for votes saying that, it doesn't work that way, okay? Because that is the example of a non-causal promise, okay? Right, jokes apart, how do we describe causality? Okay, how do we describe it in more technical terms? In order to do this, let me introduce another operation. So this is p tau, or rather, let me call it a fancy name, maybe Greek alphabets. So call it pi tau. So this we define as the truncation operation. Okay, truncation operation. What does this do? The truncation operation is something like this. So basically, if you have a signal such as this, let's say this is the 0 time axis, and if you're passing this is, let's say, u. All right. Now, if you want to draw the same signal after it has been truncated, as the name suggests, what will happen is, at this instant tau, it will be chopped off, it will be clipped. So the signal will only, sorry, this is the tau. Excuse the pathetic drawing here. So this is tau. So beyond tau, it will be chopped off. It will assume 0 values. Okay, for any value of time greater than tau, it will be 0, and the values before tau will be retained. Okay, that is what the truncation operation does. You can write it down algebraically as well as the expression for the truncation operation, but you get the idea clearly, right? So how is causality defined in terms of this? Suppose a system is specified by y is equal to gu. Again, I'm dropping the brackets and I'm dropping the argument in time. You understand that it is indeed an argument, that these are indeed signals and not just, you know, values or random variables. I mean, random numbers picked up. Okay, these are signals. So y of t is equal to g of u of t. So g is basically the operation that's being carried out on the input in order to yield the output. Okay, so if this g is what characterizes the system, then this system is said to be causal if the following, if the following holds. So what is this? It says that if pi tau g pi tau is equal to pi tau g for all tau. All right, this is very important, for all tau. Okay, what does this essentially mean then? Let's go to the next slide, explore this a bit. This essentially means that if you have a signal ut as the input and you truncate it first, then you pass it through the system, and then you truncate the output, the resultant output, that is the same as if you had passed the original untruncated input through the system and then truncated the output. So whether you pass the input after truncation or not, it does not make any difference. So if this is the case, then you call the system as causal. So if you want to convince yourself that this is indeed consistent with the definition of causality as we have defined in layman's terms, that is, the present depends only on the present and the past and not on the future, this is the way to understand it. If you are truncating something beyond the instant tau, so tau is basically any value, right? Any real value, any value of your time instant, right? So if at any time instant, whether you truncate it or not, it means that whether you're considering the values of the input beyond the value of tau or not, it makes no difference. It means that at the value, at the instant t, yeah, at the instant t, whether you have truncated it at a point or you haven't truncated it, it matters not. That means values beyond tau will not have any influence. Okay, and this is true for every tau. Okay, so for example, let's say you have this as your input. Okay? It exists, let's say, So basically 0 is just a frame of reference, right? Any instant when you start your observation, you call it as your time t is equal to 0. It does not mean that the signal cannot exist before 0. Of course, we make certain assumptions down the line and say that the system is initially relaxed, which means that at beyond the for instance of time less than 0, it is 0. But for now, we don't make that assumption. We just say, okay, this is, so 0 is just a point in time, right? So if you're truncating this, yeah, that means you ignore these values, okay? And then you pass this through your system, yeah? You pass this through G, okay? And then you get some, let's say some output. So this is basically when pi has acted on input, then this is basically G of pi has acted on the input, yeah? And now it says that if you chop this off at the same instant, let's say this is tau, so this is the original, yeah? And if you chop this off now at this instant tau, yeah, so that is basically now you're doing this, all right? And it would not make any difference whether you had passed this unchopped input or you have passed on this truncated, like unchopped means truncated, whether you pass this truncated input through the system or you pass the original input through the system, so long as you truncate at the end at some tau, it's the exact same thing, all right? So this is causality, which means that basically these future instants have no bearing on the past, okay? Even if you had allowed this input to dwell, even if you had allowed these input values to stay, instead of chopping them here using this power, pi, these things would not have changed, all right? So I hope you get that idea, at least from the figure. Now, this is something interesting. So we've seen that for, let's say, for time invariance, yeah, you need commutativity with the shift operation, all right? And for causality, we have now seen, okay, let's see that. Yeah, for causality, we have seen that this is the condition that needs to hold for every t, all right? So what if a system is for both causal and time invariant? Is there something special that we can do? All right. Okay, so that is the question we want to explore. Okay. Let's see. So you agree that from the causality condition, we have that pi of tau g pi of tau is equal to nothing but pi of tau g. Okay. So this is an operator notation. So we are not getting rid of the input. So basically, when this operation is done on the input, it's the same as doing this operation on the input. That is what it says. Yeah. Okay. Now let tau is equal to 0 without loss of generality. You can choose any value. You can choose tau is equal to 5, tau is equal to 10, anything. We're just choosing tau is equal to 0. So that then means that pi 0 g pi 0 is equal to pi 0 g. Yeah. So that basically means if you do the following operation on the signal, you get identically the 0 signal. Yeah. So this is not the 0 as in the number 0. This is basically the 0 operation. So basically you are annihilating any signal that you give. This is like a system which always yields a 0 output. So this 0 is to be read in that sense, okay? This is not the mathematical 0 as in 1 minus 1 is equal to 0, okay? This is the 0 operation. So you give any signal, it's like a black hole. It takes in everything and spits out 0, spits out nada, nothing. Okay, so that is the sense in which this 0 is to be read. Okay, so clearly if this holds for every tau for causality, okay, since we have said this is the condition for causality, if this holds for every tau without loss of generality, we let tau equal to 0, and then this is going to be true, right? Now, from time invariance, we have, what can we say? Pi, sorry, this is not from time invariance really. From time invariance, we just know that pi tau, sorry, that's a pi, right? We called it some other name. This was a shift, that was a sigma. Yeah. So time invariance, we know that sigma tau g is equal to g sigma tau. Okay. So we have the two tools. Let's say this is 1 and this is 2. Actually, we can call this as the main. Let's call this the Roman 1. Okay. This is the main condition for causality. All right. So having seen this, now I'm going to make a claim, and I shall argue that this is indeed true. So what is the claim? The claim is that pi tau sigma tau is equal to sigma tau pi 0. Okay, and I'm going to hopefully convince you that this is indeed the case. So why is this the case? So look at this something, this is very important, okay? When you're writing the sequence of operation, the sequence is very important. That is why this commutativity is exactly the defining factor behind time invariance, all right? So this sequence means that first you shift it and then you truncate it. And this means that first you truncate it at 0 and then you shift by tau. So why is this, why are these two operations equivalent? Okay? Why should this be true? Again, I'm going to do this, I'm not going to rigorously prove this, but I'm going to just draw a figure and illustrate to you that this is indeed the case. So let's say this is any signal, all right? So what if you first shift it? Yeah. So let's say this is the shifted version of that. So let's say you shift it by tau. So this gets shifted by tau. Okay. So this is basically sigma tau is acting on this. Okay. And then you truncate it, right? Then you truncate it. So basically this is, let's say, minus tau. So this is now moved to 0, and this is, let's say, whatever was at 0, that has now appeared at tau. And then you truncate it. So what this basically means, so this is basically the truncation operation, the pi tau. So what happens is this, right? Tau. So basically it means that this portion has now moved here. Although they don't look identical because of my pathetic drawing, but you must understand it in this sense, okay? So this is basically what it means to say that pi tau sigma tau. The action of pi tau sigma tau is captured through this figure. Now let's look at the other side of this. The other side is take this signal and pass it through what I shall call as pi 0. So basically when I do that, I've truncated it here. Yeah, beyond this everything becomes 0. Yeah. So I'm just truncating it at t is equal to 0. Okay. And then I do the second operation, which is what? Which is shifting by tau. So let's say this is minus tau. So now this gets shifted here to the right. Yeah. So this was the erstwhile value at 0. Now this is at tau. And this is 0. So this is basically sigma tau. Yeah. So you clearly see that these two are one and the same. So therefore, hopefully I've been able to convince you that this relation that I've written here is not a trick I've pulled out of the hat. It is indeed true. or it is indeed valid. Okay, so let me note that down. Let me put a mark against this and call this relation number 3, right? Now we combine both these properties of time invariance and linearity. So we already know that we have pi 0 g minus pi 0 g pi 0 is identically equal to 0. Yeah. So this means that pi 0 g, this is the identity operation, which means that if you give an input signal y, u, the output signal will also be u. So don't read of these as the identities that you have learned in matrices and in that sort of notation, right? So this is 0. This comes straight away. This is right out of this relation, right? This relation number 1. Yeah, I'm just rewriting it. All right. Now, if that is so, if this is identically 0, I can very well apply a shift operation on this and it will still remain 0. If this is identically 0, it means that it matters not whether I shift this or not. A zero operation means it gives a 0 signal. So 0 signal, whether you shift or play around with it, it really matters not, isn't it? I minus pi 0 equal to 0. Now, what does this mean? What is the next property I'm going to use? Now look at this and focus on this. Focus on this third relation that we have. Pi tau sigma tau is equal to sigma tau pi 0. What do you see here? Sigma tau pi 0. It's already appearing here. So I replace this here. So I replace this here as sigma tau pi 0 as pi tau sigma tau g, yeah, I minus pi 0 equal to 0. Now I use the property. So far I have only used the property of causality. Now I'm going to use the property of time invariance. So this operation commutes. Yeah. So I'm going to write this as g sigma tau I minus pi 0 equal to 0. Yeah. So that means what? That means essentially that p tau g sigma tau minus p tau g sigma tau p0. Yeah. Now I'm going to push this pi tau g, then this is sigma tau minus sigma tau pi 0 is equal to 0. Again, the sigma tau pi 0, I'm going to repeat this same operation. Yeah, this just as you had here. So this is going to be pi tau g sigma tau minus, what is this? You can replace this by pi tau sigma tau is equal to 0, which then goes on to imply that I can pull out this pi tau g, then this I minus pi tau sigma tau, yeah, is equal to 0. Yeah. Now applying, because this shift operation is invertible. Yeah. Because this shift operation is invertible, so I'm going to now argue that whether, and since this is 0, right? Yeah. So what does this mean then? I can get rid of this shift operation and it will not make any difference. You follow? So if that is the case, then I can jolly well write this expression as pi tau g I minus pi tau is equal to 0. Whether you forward shift or backward shift the 0, yeah, it doesn't matter. But what does this mean? Look, I started with the condition on causality which says that this must hold for every tau, okay? And since this holds for every tau, I'm going to just take tau is equal to 0 without loss of generality. As I said, you can choose any other tau also rather than 0, but I've just chosen 0. It could be 10, 15, 10,000, 20,000, anything. Okay, I've just chosen just this to be 0 arbitrary. And then if I'm additionally given that the condition of time invariance also holds, I come to the conclusion that if you check for, that is, if this condition is satisfied for tau is equal to 0, then it holds for any arbitrary tau. What that means is that if I had not been told that this is a time invariant system, I would have had to check this condition, that is this condition number 1, for every possible value of tau, every value of tau. And if this is true, only then I would have been able to deduce that this is causal. It's a very difficult problem then, right? On the other hand, if I know that the system is time invariant, I can just choose not just 0 but any arbitrary value of tau and see if this condition is met, and I'm done. So that is how these properties such as time invariance and causality, they have this interplay. When they're combined together, life becomes a lot simpler, and that is exactly one of the reasons why we shall focus on very special class of systems that can be open loop and closed loop, that are dynamic systems, that are linear systems, that are time invariant, that are in continuous time, that are deterministic, and that are causal. When we combine all of these values, life becomes a lot simpler, and eventually our system models will be described by ordinary differential equations, ordinary linear differential equations, such as the ones that look like these. And there's a very nice way of solving these by a technique, by a tool, which is known as Laplace transform. So why Laplace transform? To give you a brief motivation, we'll get into Laplace transform in the next module. To give you a brief motivation, you know, in the olden days, you had multiplications, right? So if you have multiplication of two very large numbers, all right? If you have multiplication, if you have the product of two very large numbers, it's not very straightforward in the absence of a calculator. So people invented log tables. So you have, let's say, m into n. So you take log of m, you take log of n, and you add them, yeah? And then you take the anti-log. So why was this action easier? Because when you take the log of this number, it becomes a relatively smaller number. When you take the log of this, it also becomes a smaller number. Then addition operation is easier than multiplication. And then you take the anti-log. Question is, who gives you what the log of a number is and what the anti-log of a number is? The answer is very simple. You have a log table. You have a lookup table, right? So that is how big multiplications or multiplications of big numbers were simplified by the use of log tables, logarithms. Something very similar happens in the solution of ordinary differential equations when they're excited by certain inputs. So you are basically given an ODE. You take the what is called a Laplace transform on both sides of the ODE. So let's say, let me go back to this. Yeah. So let's say you have an ODE such as this. You take the Laplace transform of each of these terms, and what enables you to take the Laplace transform? The fact that these systems are linear, time invariant, causal systems that allows you to take Laplace transform. That is why it is important to understand all these properties. We shall see in the next module how these properties come into the picture. So these allow you to take the Laplace transform, and because you know the Laplace transforms of some of the most common signals, just like you know the logs of the numbers from the log tables, yeah? So you take the Laplace transform and then you do some algebraic manipulations, which are easier than solving differential equations by integration, okay? So the action of integration now becomes basically the action of performing some partial fractions on some rational functions of the complex variable s, all right? So you perform some partial fractions, And then you look up the inverse Laplace table, and then you get back your time domain signals, all right? So just like logarithms simplify multiplication, Laplace transform is a tool that simplifies the solution of ordinary linear differential equations, all right, with constant coefficients. That is ordinary linear differential equations representing time invariant causal systems. So that motivates our study of Laplace transforms, which we shall begin to see in the next module. So we'll stop here today. I'll stop sharing the screen. Just a second, I'll stop sharing the screen, and hope that you'll attempt the exercises that I've given you. Yeah. Okay. So thank you all. See you at the end of the break in the next module. Bye-bye.